while I was on my working trip to Tenerife, and at a conference, and she gave a great talk. So I thought she could repeat that. So thanks so much for doing that. And her advisor is Mariska Creek, and she's at UC Berkeley right now. That's pretty much it. And if you'd like to add to that, go for it, Aliza. But
yeah,
it's all set up. So yeah.
Great. Thank you. Yeah, so I'm Aliza. I'm a PhD student actually still at Berkeley. My PhD advisor is Mariska Creek, and she was a professor here and then moved to Leiden just a couple of years ago. So that's in the Netherlands, which is disappointing, but also that means I get free trips to visit her a couple times a year. So I just got back and I ate my body weight in stroopwafels, and it was amazing. But I'm really excited to be giving this talk and tell you about the research I've been doing over the past few years. But I know that there's a few physicists in the room, so I'm going to do the best I can to give a more broad introduction to galaxies before we really get into the research side of things. So I'm going to start off the talk by showing you a picture, the first picture ever taken of a galaxy outside of the Milky Way. So this is the Andromeda Galaxy. It's our nearest neighbor. It's a very massive galaxy. And as you can see here, it's kind of spiral in structure, a little bit disky. And something that I thought was really cool is that in the book it was published in 1888, the title of this picture is Nebula Andromeda. And that's because 100+ years ago, we actually didn't know that other galaxies existed outside of the Milky Way. The field of galaxies is a pretty new field. So they actually thought that this was a star-forming region inside of the Milky Way. But of course, around 1925, we realized that there are many galaxies out there. And we've done a lot better since then. And here are some of those pictures of galaxies in our local neighborhood from the Hubble Space Telescope. Nearly all the galaxies nearby, we can see in great detail. And what we've found by looking at them in a lot of detail is that they fall into two separate camps. So at the top, we see these spiral galaxies with amazing spiral arms. And they're bluer in color, kind of like Andromeda, the picture I just showed. And in the bottom, we see that we also have galaxies that are kind of elliptical and spheroidal in shape, and they're a redder color, and they tend to live in these groups of galaxies. Now, astronomers have been studying galaxies again for decades, ever since 1925. Honestly, I think it's kind of crazy. We didn't know that galaxies existed outside of the Milky Way until then. Einstein had developed the theory of relativity at that point, and we still thought that maybe we're the only galaxy in the universe. Anyways, we've been studying these galaxies for so long, and surprisingly, we've kind of been asking the exact same questions ever since then, which is, why do galaxies today look the way that they do? And how can we explain this diversity of galaxy types? So you might be thinking these are very basic, straightforward questions. It's kind of crazy that we don't have answers yet. I mean, come on, we have this $10 billion telescope that's in space helping us understand these questions right now. And the main reason that I think we don't have these answers is because galaxies are actually super complex and messy. So they have a lot going on. In a single galaxy, you have trillions, billions, trillions of stars. You have multi-phase gas, you have really cold gas, you have really hot ionized gas. You have a supermassive black hole at the center of every galaxy that's accreting, sometimes at very high rates and emitting lots of radiation. These galaxies live in dark matter halos. And then, of course, those halos lie in the larger cosmological context. And so these processes occurring in a galaxy are very hard to model because we're talking about length scales that range from a single atom all the way to the entire size of the observable universe. And also, we're looking at timescales that range from super fast subatomic processes all the way to billions and billions of years of cosmic time. So it's really hard to model and answer these questions just through modeling. And really the best way we can learn about these galaxies is by observing them directly. So again, when we do that, we find that galaxies really fall into two types, these spiral galaxies, like the one I'm showing here, and the more elliptical galaxies. To put these qualitative categories into some more quantitative terms, here I'm showing the distribution of galaxies in the nearby universe. So on the x-axis is the stellar mass of a galaxy, and on the y-axis, I'm showing something that we call the color of a galaxy. And what that is really just a comparison of the UV light to the optical light coming from the galaxy. Now, galaxies with really young stars, they shine really brightly in the UV. And so you can kind of think of this color as a proxy for the ages of the stars in the galaxy. Okay, so when we look at hundreds of thousands of galaxies, we find that their distribution actually is bimodal. There's two loci. And so they're either old and massive and red, or they're blue and less massive. They're blue and less massive and young. So astronomers are actually really good at naming things. So these two loci are called the blue cloud and the red sequence. Now, galaxies in the blue cloud, they tend to be not only very young and less massive, they also are usually spirals, and they're disky, and that's owing to the ordered rotation of their stars and their gas. On the other hand, galaxies on the red sequence, not only are they massive and old, they also are gas poor. They're elliptical in shape, and they don't have the same ordered rotation. They're instead more pressure supported. And key is that the galaxies in the blue cloud are actively forming stars, whereas galaxies on the red sequence are no longer forming stars, and they kind of appear to have not been forming stars for billions of years. So really, these galaxies on the red sequence, the massive elliptical galaxies, are kind of the fossils of cosmic evolution. They're kind of the relics or the endpoint, you can kind of think, of the entire history of galaxy evolution. Now, understanding the origin of this bimodality has been the driving question, or a driving question, in galaxy evolution for decades. And the most common way to approach this question is by looking at nearby galaxies in incredible detail. But that kind of only gets you so far, because especially for these fossil galaxies, because it's really challenging to infer their formation and assembly histories just by looking at fossils. It's hard to imagine what a dinosaur looked like just by looking at its fossils today. But luckily, unlike archaeologists, we as astronomers have another tool, which is a time machine, thanks to the speed limit of light. So we can look far away into space, and that's the same thing as looking far away into time. So when looking at the distant universe, we can actually directly observe the progenitors of these galaxies as they are forming, which is awesome. And actually, for a long time, we didn't think we could do this. And that's because in order to see the progenitors of these galaxies, we have to look really far back into the history of time. And those galaxies are very faint. It's hard to see them above the noise. And we also have this pesky atmosphere above us. And so it's kind of hard to observe these things. But luckily, in the 1990s, the Hubble Space Telescope launched, and it really gave us the first look at galaxy formation in action. And it transformed our understanding about how galaxies form and evolve. But unfortunately, the Hubble Space Telescope can only look so far, and that's primarily due to this thing called cosmological redshift, which is that the light from distant galaxies, not only does it take forever to get to us, but it also gets redshifted as it travels. And Hubble was not optimized to see this redder, namely infrared radiation. So Hubble's limit is actually here, it's at 1.6 microns, which just stops short of the formation of these massive galaxies. And in order to see these galaxies, we need to look even further not further into space, but also further into the red wavelengths. And so for those of you that have maybe lived under a rock for a few years, we now have this telescope. It's called the James Webb Space Telescope, and it's allowing us to peer into the distant universe. And actually, one of the primary science goals was for this telescope to observe the formation of the first galaxies. So a little briefer on this telescope. It's huge. It's the most complex telescope, most powerful telescope ever built. It has 18 segmented mirrors and this kind of tennis court sized sun shield. And this sun shield is key because, of course, we're trying to detect infrared light from the first galaxies. And the Earth and the sun shine in infrared, so you need a shield that can protect the very sensitive instruments from this heat. So launching a tennis court-sized telescope into space is actually a very challenging thing to do. And because of that, they had to fold up the telescope, like you see here, for its launch, and it had to deploy and unfold after it got to space. And that means that it had 344 single points of failure when it left the Earth. And that was very terrifying. I'm sure many of you watched the launch, but the launch actually went perfectly, almost exactly as planned. And they added extra fuel to the telescope just in case the launch didn't go well, because they can use the fuel to kind of correct some things along its way. But because it went so perfectly, there's a lot of fuel left over, which means that not only are we going to observe the expected 5 years, do astronomy for 5 years, we can actually use this telescope for now 20 years, which is great. I actually was very worried, like, how are you supposed to do all of the science that they're planning to do in only 5 years of telescope time? So that's good news. Anyway, so this amazing telescope is already beaming down some great data to show you how amazing this data is. Here's a picture of the Large Magellanic Cloud from the now retired Spitzer Space Telescope. And JWST is observing with similar wavelengths. So we can directly compare these two images. And here's what JWST sees for the same exact patch of sky. The improved sensitivity and spatial resolution just gives you like this amazingly clear image. And you can now start to see these dust lanes and all the gas and individual stars way in the background. So this is great. JWST was launched now already a couple of years ago, and we're already doing some amazing groundbreaking science. I think some of the most exciting galaxy results that have really come out from this telescope is from groups that have just stared at the same patch of sky for a very long time and just integrated for a very long time on a very small patch of sky. So this group did that. They're called the JADES group, and they stared at this one thought to be blank part of sky for a very long time. And instead of finding nothing there, what they found was tens of thousands of galaxies. So let me zoom in for you. This region here, when I look at it, I see maybe like 1, 2, there's a few stars. So the ones with weird diffraction spikes, there's a few stars, but everything else in this image is an individual galaxy. Like every single speck you see here is an individual galaxy with billions of stars. And like I explained earlier, all of these galaxies, we're observing them at different points in time. So like the light from this galaxy here, it's a little bit bluer, it's bigger. It probably took about 3 billion years to get to us. But then if you look at these really small red specks, those galaxies, their light probably took about 13 billion years to get to us. So in a single shot, in a single patch of sky, we can actually look at the entire history of the universe and the formation of galaxies over the last 14 billion years. So in the last year or so, from these sorts of deep surveys, there have been some amazing, exciting discoveries. One of my favorites is that they found there are a surprising number of really massive galaxies 12 billion years ago, that's only like 2 billion years after the Big Bang, that were not forming stars. So not only is it weird that they're already so big, but it's also weird that they find many that are not even forming stars anymore. Now that's surprising because like 2 billion years after the Big Bang, there's a lot of gas around, and all the galaxies around these are actively, vigorously forming stars. So to actually put this into context, it was even surprising about a decade or two ago when Hubble discovered that there were galaxies only 6 billion years ago that weren't forming stars. That was surprising to us even then. So now 12 billion years ago, that's like just kind of mind-boggling. A second also relevant discovery that was actually first made with Hubble and has since been confirmed with JWST is that these distant massive galaxies that are no longer forming stars, they appear to be much more compact than the galaxies that we see today, the giant elliptical galaxies. So here on the left, I'm showing galaxies about 10 billion years ago, and they're super compact compared to the extended ones we see today. And that's surprising because these galaxies are no longer forming stars. So how can you explain their size growth if they're not even adding more stars by just growing them themselves? So combined, these two puzzling discoveries over the last few decades have inspired the theorists, and they've come up with this idea of how massive galaxies have formed over the last 13 billion years. And it looks something like this. So after the Big Bang, galaxies started forming, and those that are in big dark matter halos, they have super high accretion rate and they build up a large stellar mass very rapidly, vigorously, and in big bursts early in the universe. Then at some point, we observe that these galaxies stop forming stars, likely 6 to 12 billion years ago. And there are a lot of theories out there about what could possibly be doing this. One is a feedback effect, like when you're creating all this gas in the early stages over here, you have this supermassive black hole at the center that's also accreting a lot of material. And when that heats up, it can actually end the star formation. Whatever the mechanism is, it appears that what's left behind are super compact galaxies that aren't forming stars. Then we think over the last 10 billion years, as I said, these galaxies have grown in size, and we think that's because they're experiencing mergers. So they might be merging with other galaxies, likely also smaller galaxies. And those galaxies add stars to the outskirts and kind of puff up the halo of the galaxies. And what that leaves us with is today, large elliptical massive galaxies. But there's a lot of questions along this whole process, of how do we explain all of these things? The first question, which relates to the star forming phase, is when and how did massive galaxies form? The second question we still don't fully understand is why do galaxies stop forming stars? And the third question is we still don't really understand the mechanism by which galaxies are growing. We don't have proof that it's mergers, it's just a theory that we have. So even with the amazing James Webb Space Telescope, we've actually still ended up with more questions than answers and haven't really solved these puzzling questions. If my talk title didn't give it away, I think that a promising direction moving forward is looking at the chemical properties of these galaxies across each of these different phases. So chemical properties, the chemistry of galaxies is really intimately linked to every step. It's kind of woven into the fabric of galaxy formation. So in the early stage, chemistry tells us something about the star formation. After the Big Bang, you only have hydrogen, helium, some lithium, and then it's really the stars that are forging all of the other elements we have in the universe. So we can see how many elements a galaxy has, and we can kind of infer something about how it formed its stars. We can also learn about how galaxies stop forming stars. We call this star formation quenching. We can also learn about mergers. When you have a galaxy with another chemical property, different chemistry, and it combines with your massive compact galaxy, the end result is a galaxy that doesn't look like either of the two, it's some mixture of them. So by tracing the chemical properties over time, you can actually kind of infer the merger history of galaxies. Okay, so I hope I convinced you that chemistry is a promising direction. But then the question is, how are we supposed to measure abundances, elemental abundances of galaxies? Well, the best tool that we have is a galaxy spectrum. So the spectrum shows the light, or on the y-axis, the flux density from a galaxy as a function of wavelength. On the left, I'm showing a spectrum of a star-forming galaxy, and on the right, I'm showing a spectrum of a massive elliptical galaxy. Now, their spectra look very different. On the left, the star-forming galaxy has these booming emission lines, and those emission lines are actually recombination lines coming from ionized regions. And the ionization is supplied by super hot, massive stars, and those stars are very short-lived. So for older galaxies, like the ones elliptical galaxies, they don't have this ionizing radiation because they don't have these hot stars, and therefore they don't have emission lines. So what are we supposed to do? How are we supposed to measure the chemical properties of these galaxies? Well, luckily, if you look closer, we see that the spectrum is actually littered with absorption lines. They're just super hard to see. They're really faint. And these lines actually originate from the atmospheres of the stars instead of ionized gas. And because of that, actually, these measurements from the atmospheres of stars are more informative, because stars preserve the chemical properties of the gas that they were formed from at the time and place that they were formed. So by looking at the properties, the chemical properties of the stars, we can actually kind of learn about the history of the star formation. Whereas with gas, you don't really get that kind of information. So for the rest of my talk, I'm actually going to be focusing on these galaxy fossils where we can measure the compositions of the stars. Okay, so in the nearby universe, what have we found already? relating to chemical properties. So one way that astronomers quantify the chemical abundance, the elemental abundance of galaxies, is through a quantity known as the metallicity, which is defined as the abundance of all elements in a galaxy besides hydrogen and helium. So that's basically all the elements that are fused in stars. And also, astronomers call every element except for hydrogen and helium a metal. And in the local universe, this metal content of galaxies, it scales directly with the stellar mass of the galaxy. So more massive galaxies are more metal rich, as you see here. And as the story goes, that's because more massive galaxies, they have deeper potential wells. And so they're better at holding on to metals. Like when you have supernova that are exploding and sending metals out into space, if your galaxy is massive enough, it'll retain those metals and keep it in the galaxy. Otherwise, they can just leave the galaxy and not end up in these measurements. We also find that galaxies that are more massive, they have higher alpha to iron ratios. What even is an alpha to iron ratio? Well, alpha elements are oxygen, magnesium, silicon, calcium, titanium. They're the elements that are produced in massive stars, in the very cores of massive stars, and they're released through core collapse supernovas, so very big stellar explosions. But what does this ratio tell us about the galaxy? So I have a nice little cartoon that illustrates this. And I thought about whether I should show this or not, but I remember learning about this my first year of grad school, and I thought this was a really cool thing that we as astronomers can do, is using this ratio to tell us about how quickly a galaxy formed. So hopefully you'll find it cool also. So the most important thing to remember is that each star in a galaxy, like I said earlier, inherits the chemical composition of the gas that it was formed from. So in this first example, we formed the stars in this galaxy over a very short period of time. And the yellow suns are the supernova explosions, releasing alpha elements. And then, after about a delay time of 30 million years, we start to see the first type 1a supernova, and those enrich the ISM, the galaxy gas, with iron peak elements. In the extended star formation period, we're now forming stars over longer times. So this top example, all the stars here, they're all yellow. They didn't form after the onset of type 1a. And so for the most part, they're going to have very little iron, and that results in high alpha to iron ratios. Whereas in this long extended period of star formation, you're forming stars well into this type 1a onset phase. And so those stars will have a lot of iron in them. And on average, they'll have lower alpha to iron ratios. So really, we can use this ratio as a tracer of how quickly a galaxy formed. And galaxies that are more massive formed much more quickly. We also find that galaxies in the local universe, the more massive they are, the older they are. So they assembled their stars earlier in the history of the universe. So altogether, we can come up with this picture of galaxy formation. And here on the x-axis is the time, the look-back time. So on the right is Big Bang, and the left is today. And the star formation rate is on the y-axis. And the most massive galaxies appear to have formed their stars in the early history of the universe, and they stopped by about 8 billion years ago. And progressively less massive galaxies form their stars over longer periods of time later in the universe. So this is great. We now understand how massive galaxies form as a function of their stellar mass. But actually, the story is kind of incomplete. And that's because we're trying to understand the formation of galaxies that stopped forming stars like 8 billion years ago. And it's hard to imagine that these galaxies haven't experienced any mergers or late-time star formation that could have affected the trends that we see, like I showed in the last slide. So one way that we can confirm that this picture is correct is by looking at even more distant galaxies. So looking back in time. And if we find that the trends are different, we actually can use that and see how they evolve over time to infer how these galaxies have grown over the last, so many billions of years. Okay, so let's go look at more distant galaxies. Let's say galaxies like 10 billion years ago. What did they look like? What did these trends look like? Well, unfortunately, we actually haven't measured trends like these for any galaxies or sample of galaxies beyond the local universe. And the reason for that is because as I showed before, spectra are super faint. And these little wiggles that we're trying to look at are super, super small, and they're hard to get enough signal to noise in order to measure them properly. So this was like moving to further distances was pretty much impossible until very recently. Now we have both the James Webb Space Telescope, and we have more efficient ground-based spectrographs on some of the best telescopes that are allowing us to start to look out further and further into the universe. So these are the different surveys that are actually going to take us to farther and farther look-back times. On the top, I'm showing the look-back time, where on the right is the Big Bang and the left is today. The extent of these boxes show the surveys, which galaxies they'll target, where in the history of the universe. And I just presented on galaxies that were close by from the SDS survey. And for the remainder of the talk, I'm going to take you on a little walk backwards in time. So our first stop is going to be looking at galaxies 6 billion years ago. So these galaxies are taken from the Legacy survey, which is a very recent ultra-deep spectroscopic survey. It had about 4,000 galaxies that they targeted that are all about, their light took about 6 billion years to get to us. And they observed for like 20 hours per galaxy on VMOS, which is a spectrograph on the VLT, the Very Large Telescope down in Chile. And here's what 2 of those spectra look like. So for those of you that don't stare at these all day, this might just look like a noisy spectrum. I know I did when I first looked at these, because it was my first time doing this. But here is how we fit the spectra. These are our full spectrum fitting code that we use, and we allow for variation in individual elemental abundances, and we have these models that we fit to the data. And when I blow this up, what we see is that actually our models are recovering every single wiggle for the most part, and all of these wiggles are real. They're not just noise, which I think is just kind of crazy. And that's owing to the 20 hours that were spent on every galaxy to get these high quality spectra. So I went and picked 135 galaxies from the 4,000 that were in the sample, because I specifically wanted to know about these galaxies that are no longer forming stars, and the most massive ones. And the first thing I did was, okay, I'll measure the metallicity, the elemental abundance, and see if we find a trend with mass like we do today. So do we find that the metallicity scales with the stellar mass of galaxies? So here are those plots from the galaxies at 6 billion years ago. And the x-axis is the stellar mass. And on the left, I'm showing the magnesium abundance. And on the right, I'm showing the iron abundance. And these are 2 elements that are commonly used just to trace the overall metallicity of the gas. So you can kind of think of them as just the total metallicity. And what we find is that the stellar mass is not correlated with either of these elements. So the mass metallicity relation appears to be flat. I was kind of surprised at first when I saw this, but then I thought a little bit harder, and I was like, okay, well, we're looking at a very small range of stellar mass. We only have the most massive galaxies. And when we look at what was found in today's universe, this is the stellar mass range that we're looking over for the galaxies in the Legacy sample. And it actually has this turnover where the mass metallicity relation flattens at the highest masses in today's universe. So our result is actually consistent with what was found today. So the galaxies 6 billion years ago appear to have the same trend. Something else that's found in the local universe, in addition to this mass metallicity relation, is that while this trend, it turns over at the highest masses, it actually is very well correlated still with size. So the size of the galaxy, how big is the galaxy? So the x-axis is going to be mass over radius, and the y-axis is still metallicity. And we see that we have the strong correlation. So I was curious if we find the same thing at earlier times. So I went out and I measured the sizes of all the galaxies, and I'm going to change the x-axis now to mass over radius. And we actually find the same thing. Galaxies 6 billion years ago, they behave the same way. We also find this strong correlation when we take into account the sizes of the galaxies. But what does this mean physically? Well, if you think about it, the M over R, this M to R ratio, is telling you a higher M over R are for galaxies that are more compact. And it's also proportional to the escape velocity of a galaxy. So this fits in actually really well with the picture that galaxies that are more compact or have a higher escape velocity are better able to hold on to the metals during supernova explosions, or even just very high stellar winds. So they stay in the galaxy and they cause the galaxy to then have higher metal quantities. So far, galaxies 6 billion years ago, they pretty much look the same chemically as they do today. But what about other elements? So I've only been really talking about iron and magnesium, but there are other elements. And they're really hard to measure though, because iron and magnesium, there's a reason we only look at those so far, and that's because they have very clear absorption features. Whereas the other elements, they're very subtle and it's hard. You need really high signal to noise data in order to even pick out the little wiggles from the other elements. So what I did is I took all of the spectra from this sample of 100 galaxies and I stacked them all together to make one very high signal to noise spectrum. And I actually did this for 4 different bins of stellar mass. So there's 4 spectra here. At first, I want you to just notice how beautiful these are. They're like they look perfect. They're these beautiful wiggles and the models have great fits. Second is how hard this is. Like you probably couldn't even tell that there were 4 spectra there because they're all on top of each other. So this work is very subtle. You need to really have the high signal to noise to pick out the slight variations between each spectrum. You can actually pick out these variations if you take the ratio of all these spectra that I just showed up here. And then you can start to see that they do indeed look pretty different. You can tell they're different. Okay, with these beautiful spectra, I was able to constrain about 11 elements from these galaxies. And here's what they look like. On the x-axis is the stellar mass. The y-axis is abundance ratio. So X is the element listed here and then over iron. And I split them into 3 categories, kind of corresponding to the nucleosynthetic mechanisms that produce them. And I don't have time to get into the results, but what we are finding is that they are consistent with galaxies today. So all this is painting a picture where galaxies 6 billion years ago, they appear chemically very similar to what we see today. But that's not that surprising because we selected these galaxies to be non-star forming, which means if they're sitting around and not forming stars already 6 billion years ago, they probably just sat around until today and they look the exact same. But what if we look further back in time? So at some point, I'm expecting that these galaxies must have looked different. So now I'm going to show you what we know currently about galaxies 9 to 11 billion years ago. So again, stellar mass is on the x-axis, and we have various properties on the y-axis. The black line here is the results from galaxies today. And these 1, 2, 3, 4, 5 individual points are the only existing individual measurements that we currently have of galaxies that exist 9 to 11 billion light years away. So we can't really say much about the population this far into the history of the universe. And actually filling in these diagrams is the primary motivator for the heavy metal survey, which is our next stop along the way. So that was legacy. We're now going to wander over to the heavy metal survey. So the heavy metal survey targeted 11 galaxies that were non-star forming about 9 to 10 billion years ago, and then 10 at around 11 billion years ago of cosmic history. So in total, we have 21 massive quiescent galaxies. So remember, quiescent is non-star forming. And we observed them with the Keck telescope. And these galaxies, their light took 9 to 11 billion years to reach us. And we observed each one for 17 to 30 hours in total with the Keck telescope in Hawaii. And I'm actually sitting right now in the observing room at Berkeley. I only got to go once to Hawaii because then the pandemic happened. And so I've spent a lot of time in this room doing many of the observations during my PhD for this project. Also, one night we stayed up really late and we were kind of like loopy and we started naming all the galaxies after heavy metal bands. And so like one of them is called Metallica, and it's the one that we found to be the most metal rich, and Baby Metal was the smallest one, and etc. But that's not going to make it the cut in the paper, unfortunately. Anyways, so we fit these galaxies with the same stellar population models. So that's the red line. And we were able to measure the amount of magnesium and the amount of iron in these galaxies that are 10 to 11 billion light years away. And here's what we found. To remind you, this is what the state of the field kind of looked like before the survey. And now with these measurements, we are really starting to fill in these diagrams. We've more than tripled the number of galaxies with these sorts of measurements at these distances. So I'll note that the uncertainties on these measurements are like pretty big, and our sample stars are still pretty small. But what's clear is that galaxies 10 billion years ago had lower metallicity than the galaxies today, which is the black line. They also had higher alpha to iron ratios for the most part, and they formed very early in the history of the universe. So today they would be observed as very old. To make this a little bit clearer, this like evolution across cosmic time, I'm going to now change the x-axis to distance away, and I'm taking the average from each of the surveys I just talked about and plotting them as a function of their distance. So for example, the SDSS survey, the distance is about 1 billion light years away maximum, and the heavy metal survey is 9 to 11 billion light years away. Remember that translates into a look back time where these galaxies, we're observing them as if they were 11 billion years in the past. And so now it's very clear that these galaxies, they've increased their metallicity over cosmic time. They've also decreased their magnesium to iron ratio. And remember, magnesium is an alpha element. And these galaxies have formed later and later in cosmic history. So this evolution is kind of surprising because galaxies, they were selected to not be forming stars. So how is it that their individual elemental chemistry is changing over cosmic time? So we finally are finding this, that their chemistry is different. They are different than galaxies today. But that's confusing because they're not forming more stars. They're already dead. So how can we explain this? Well, and I did want to also show that, remember that the magnesium to iron ratio, remember that that's related to how quickly a galaxy forms its stars. So we can take this magnesium to iron ratio and we can actually translate it into what we think the star forming history of these galaxies were. And what we find is that galaxies from the heavy metal survey, they formed their stars in super narrow bursts of star formation very early in the history of the universe, whereas galaxies today, on average, they form their stars at much later times and over much longer timescales. So again, this is surprising because these galaxies should be the same, but we're finding this evolution. So how do we explain this? Well, I'm going to argue that this could possibly be an observational bias. So when we select this sample from the heavy metal galaxies, when we select the sample, we are requiring that these galaxies, these distant galaxies, form their stars in the first few billion years of cosmic time, and that they're already not forming stars. So we're biased towards galaxies that formed over very short periods of time. Whereas galaxies today, we allow now galaxies in our sample that maybe took their time to form, and they then stop forming stars later in the history of the universe. To demonstrate this idea, I made a little cartoon. And here is our little cartoon universe. And 11 billion years ago, most of these galaxies were forming stars. Down here, I have our two plots, the metallicity and the magnesium to iron ratio, the star formation timescale. And maybe one galaxy at this time stopped forming stars. And that puts it somewhere over here. Remember, it's very early in the universe. They haven't had much time to incorporate type 1a products. So they have very low amounts of iron. They have low metallicity. That also means that they have very high magnesium to iron ratios. So again, they formed over very short periods of time. Okay, then a few billion years later, the galaxies have grown in size. And now we're going to make some of them stop forming stars, and they're added to our sample. And those ones are going to have a little bit higher iron abundance or higher metallicity because they've had more time to form stars. And then again, we're going to fast forward to today. Galaxies have continued to form stars, and now our sample has grown by quite a lot. So we now, in today's universe, we would have a sample that includes 1, 2, 3, 4, 5, 6, 7, 8 galaxies. And on average, they'd follow this black line. But they have this scatter that ranges to very low metallicity values. So to confirm this picture, all we have to do is look into today's universe and say, hey, wait, do we find galaxies today that have small sizes and that are metal poor and that have high magnesium to iron ratios. And if we can confirm that these galaxies do exist, then we can kind of just chalk this up to an observational bias, and that these galaxies are just kind of sitting around doing nothing until today. So I went out and looked for these galaxies. Here is a sample of galaxies in today's universe from the SDSS and massive surveys for a range of stellar masses. And if this is just an observational bias, these are the galaxies that we should that should correspond to what we're seeing in the heavy metal survey. So now when I plot the heavy metal survey on top, we actually see that there's a lot of galaxies that fall below what we see today. So they can't just sit around and do nothing till today because we don't see them in today's universe. They're absent. That means that the observational bias can't explain all of this evolution that we're seeing. Instead, something has to affect the individual galaxies, mess up their chemical properties, and help them reach the values that we see in today's universe. One way you can do this is through mergers. So by merging with other galaxies that have maybe formed stars over longer times, you can incorporate those stars into their galaxy, into their halo, and then their average properties will be different by today. And remember, this was actually one of our theories of how massive galaxies form over time, is that over the last 10 billion years, galaxies have merged with other galaxies, causing them to grow in size. And now possibly we have evidence that it's also causing them to change their chemical properties. Okay, so in order to confirm this picture, I'll again say that these individual measurements, they have very large uncertainties. We also have very small sample sizes, so we can't say anything for certain yet. And what we need to confirm the story is a larger sample size of galaxies with higher signal to noise ratios. And luckily, we have an approved JWST program, and we're going to get the data actually in like the next month or so. I'm kind of stressed about it. And we're going to be observing 18 massive galaxies that are no longer forming stars from between 8 to 12 billion years in look back time. So just a little briefer, here is an example. This isn't one of the galaxies we're looking at, but it's an example of what they will look like. We're going to have an amazing spatial resolution, and we're going to get these beautiful spectra. So this is just a simulation that I did for the proposal showing how high signal to noise we're going to get from the spectra from JWST. And not only will we get just a single spectrum for a galaxy, but because of the incredible spatial resolution, we can start to measure the chemical properties across the entire face of the galaxy. And that will tell us something different about how these galaxies have assembled at earlier times. So more about the earlier parts, of the galaxy formation. And so I'm really excited for this program. It should be coming in the next month or so, and stay tuned to see what those results will look like. So with that, I'm going to put up my conclusion slide and just summarize that, the heavy metal survey has really shown us that massive galaxies that are no longer forming stars, they appear to need some sort of mechanism that acts on the individual level to alter their properties to match them with what we observe in today's universe. We also find that galaxies only 6 billion years ago from the legacy survey, they look very similar to the galaxies today. So nothing really needs to change in their chemical properties for them to align with what we now see today. So really it is between the last 12 to 6 billion years ago that something needs to happen. And again, really looking forward to these spectra. So stay tuned, and thank you.
Very cool. Thanks for that talk. Question. Chris.
Thanks for that talk. That was awesome. I'm thinking on the fly, so if this doesn't make sense, just shoot it down, okay? In order for you to have how did you call it? Late time star formation, right? You'd have to extend the period. That'd be something like, I don't know, for star formation to take effect, you have to have cooling of gas, and maybe, I don't know, maybe AGN in these early galaxies are keeping the gas too hot. Does that make sense? Could that be a possible thing rather than, like an observational bias or something?
Yeah, so we don't think it's fully an observational bias now. And you're right. We think so the mergers may be they're bringing in different stars with different chemical properties, so that can affect what we see. But also with mergers, you might be bringing in colder gas that can then form stars out of a mixture of the gas they brought in, plus some of the gas that's already in the massive galaxy that's already not forming stars. So really you could have both mergers, and you could have late time star formation, and you could have this observational bias all contributing to this evolution that we're seeing here. We think it's a bit of each of those.
Isn't that always the case?
So if memory serves, the early formation models that had chemical evolution for elliptical galaxies relied upon this escape, the depth of the potential well as the kind of the driver, and had as a prediction quite steep chemical gradients. So they should be very metal rich toward the middle, and then I think it could get as high as 10 decks per decade or something ridiculous like that. And then mergers would, they would destroy that over time. They would shallow that out and destroy that signal. So this could be so basically let me stop there and ask you if you have a comment on that, if that agrees with what they're saying these days.
Yeah, I think that idea still holds true generally, that like the integrated value goes with the stellar mass. But I think the gradient that we see in galaxies now we think may no longer just be a factor of the potential energy, the escape velocity changing as you go further out. And now might be that actually these mergers, if they're small enough galaxies and you're accreting just these small minor mergers, they actually can be deposited into the outside of the galaxy. And so the outskirts would then be less metal rich because those stars originated in way less massive galaxies. And so you can increase the gradient over time by adding these small satellite galaxies with low metallicity to the outskirts. So something we can do is look at, like what I'm really excited for with JWST is now we can actually look at earlier times before these mergers even happened. Do we see the same gradient? And if we do see the same gradient, then we know that it must be less of the mergers and maybe more of this like gravitational potential effect.
Galaxies are complicated, aren't they?
They're so messy.
Anything else?
Is there anything on Zoom? Any questions on Zoom?
Oh yeah, that's a good point. Any questions on Zoom?
Yeah, can I ask a question?
Absolutely.
Thank you for that awesome talk and really nice data. In our Astro Journal Club this week, we were reading a paper that talked about a surprising number of massive black holes in compact red galaxies at high redshift. And I was wondering if you've come across any AGN or have thought about black holes in these galaxies at all?
Yeah, actually one of the galaxies in this heavy metal survey, so we have 21, 2 of them ended up being AGN. There wasn't really a way for us to like select that in our initial selection. And one of them is actually a post-starburst galaxy. So it looks like it recently quenched within the last billion years or so. And it has this big AGN. So like, correlation isn't causation. But we do think that definitely the size of the black hole and whether it's being able to power enough radiation to quench the star formation, we think that is related then to the galaxies that we see that aren't compact and not forming stars. I don't know dynamically how it's related, but that's our feeling from the star formation perspective.
Awesome, thank you.
Let's thank Aliza again. Thank you so much.
Thanks for having me.